Good morning, everyone. Back to AP Physics 2. We're going to start with thermodynamics today. We are going to be forever until the end of time. Every science you ever take will use the Kelvin scale. So why is that? Why is the Kelvin scale so important and so unique? Well, that's because the Kelvin scale is defined where 0 degrees Kelvin is absolute zero. Okay? Now, you probably don't understand the significance of absolute zero, but you will once we get into the laws of thermodynamics, okay? For a brief description right now, absolute zero is the temperature at which a system has zero energy, okay? It has zero heat. There is nothing in the universe that could be colder than absolute zero, and that's the gist of the third law of thermodynamics. You can never reach absolute zero. And we'll get a little further into what that means and what that is in just a few moments. So that's the gist. The Kelvin scale, degrees Kelvin, is what we will always be using in this class. Now, every now and again, you're going to get a problem that gives you degrees Celsius. Oh no, time to panic. I don't know how to convert. Degrees Kelvin equals degrees Celsius plus 273. It's that simple. I don't believe that's on your reference table. I think that's going to be something you need to memorize. Let's get into the meat and potatoes of this unit. So first we're going to start with gases and ideal gas law. So first we're going to need to establish a sort of a conceptual understanding of what exactly is a gas. Okay? We all know that the gas is the third state of matter, and it is the matter that it is the state of matter that you need to input energy in order to reach, okay? Water is the best example of this. In its standard state, in room temperature, water is a liquid. We need to put in energy, we need to add heat to the water in order to cause it to boil and cause it to form a gas, which we call steam, okay? So gaseous water, I'm going to write it as H2O sub G because I'm a chemist. If I had a container of gaseous water, I'd have a bunch of different water particles floating around in here like a gas, okay? And the difference, the quantifiable difference between the water and the gas is because when you add heat to a system, the heat breaks the attractions between the molecules, okay? So in its liquid state, water it feels attractions to the other water molecules. That's how the water molecules stick together in a liquid state, because the water molecules are attracted to each other. When you add heat to the system, those attractions break. And when the water molecules are no longer attracted to each other, they're free to float around into space, which creates the gas, okay? So that is an important characteristic of an ideal gas. Particles are not attracted to one another. So what that means is that in this depiction here, the particles are not still. They are not static. They're constantly bouncing around, they're constantly moving, they constantly have some velocity, and in that they are colliding with each other, okay? If the particles were attracted to each other, then when two particles collide, they would stick together. Or when two particles collide, they would bounce off with less energy than what they started with. Okay? So that is an important distinction because it says that in every collision between two particles, two particles bounce off with exactly the same kinetic energy that they started with. Okay, which is only true when the particles are not attracted, which, if you remember from AP Physics 1, is what we call an ideal or perfectly elastic collision. Another characteristic, collisions are elastic. For another characteristic of an ideal gas, we're going to have to reference back to the Kelvin scale that I just introduced to us. Okay, another characteristic of ideal gases is that they are at sufficient temperature such that the particles have enough kinetic energy to continue moving, continue bouncing around at very high speeds, okay? Now, a concept that you may not be familiar with is that temperature is proportional to, that's what this symbol means if you've never seen it before, is proportional to the total energy of a system. Okay? So as the temperature of something rises, so does its energy. Okay? The temperature of a gas, by definition, is the average kinetic energy of the particles in that gas. Okay? Let me say that again. The temperature of a gas is the average kinetic energy of the particles in the gas. All right? Which means as you decrease temperature, the particles move slower. Okay? In order to maintain the assumptions in ideal gases, we need to stay at temperatures high enough to maintain good kinetic energy. So the Maxwell-Boltzmann distribution is a name that all my chemistry friends have heard, but let me explain what it is. A Maxwell-Boltzmann distribution is a table, it looks like this, okay, where on the y-axis you have percent of particles, and on the x-axis you have kinetic energy, okay? So here you can see that our table looks like a bell curve. What is this telling us? It means that, first of all, not all the particles in the gas have the same kinetic energy. They don't all move at the same speed. Kinetic energy of the particles exists on a bell curve, which means there exists a average kinetic energy right in the center. The average kinetic energy is the most common, the most frequent kinetic energy in the gas, okay? But at the extremes, you're going to have some small percentage of the particles that are moving exorbitantly faster than all the others, and you're going to have some small percentage of the particles that are moving very, very, very slowly, okay? So it exists on a bell curve. So we are given an equation that helps us better quantify the kinetic energy of particles in relation to temperature. And we are given on our Physics 2 equation sheet, third page that is, that the kinetic energy is equal to 3/2 times the Boltzmann constant, K sub B, times the temperature of the system, okay? The temperature of the system is in units of Kelvin, okay? Don't plug Celsius into that, I will hurt you. Okay, so let's, you know me, I always like to pay attention to the units of the things I'm plugging in, because that helps me understand my equation much more deeply, okay? Kinetic energy on the left, I'm given units of joules equals 3/2, a constant, times the Boltzmann constant, which is present on the first page of your reference table. Boltzmann constant is in the top left-hand corner, which is 1.38 times 10 raised to the negative 23 joules per degree Kelvin, okay? So I have units of joules equals units of joules per degree Kelvin multiplied by units of Kelvin. Okay, my units agree. Good to know that. Anyway, this Boltzmann constant is going to be useful for reasons outside of this equation as we apply it further along, okay? Back to our equations for thermodynamics, like I said, are on the third page of your reference table. We have another equation that we use to describe ideal gases. My chemistry students are going to recognize the first two parts of this. PV equals nRT equals nkBT. N times the Boltzmann constant times temperature. Okay, so let's explain what this equation is. Capital P, as we should remember from the fluid dynamics unit, represents pressure. Capital V represents volume. Lowercase n represents moles. For my non-chemistry students out there, moles are a unit of particles, okay? 1 mole equals 6.022 times 10 to the 23rd particles. That number, 6.022 times 10 to the 23rd, is on your reference table. That number is called Avogadro's number, also on the top left-hand corner of the first page. Which means 1 mole still has units of particles. We are just saying that we don't want to count up all the atoms in our gas. If I have I don't know, 6 billion trillion particles of water in my gas, I don't want to write that all out. So that's the purpose of the unit of the mole, okay? I don't want to write, I have 6 times 10 to the 23 particles in my system. I just have 1 mole of particles in my system, okay? So lowercase n is the amount of moles you have. Capital N is the amount of particles you have, okay? So they are 2 quantities that represent the same thing, and they differ by a constant, okay? So if you want me to recrystallize it for you, you'd say that there's 1 particle of Meek right now, and therefore there is 1 over 6.022 times 10 to the 23rd moles of Meek right now. Okay. So given that equation, that real introduction of moles, you can say that pressure times volume equals the moles times R, which is your ideal gas law constant. The ideal gas law constant, also present on your reference table. So universal gas constant is on the left-hand side of the first page of your top left-hand corner of the first page of your reference table. And in the Physics 2 course, we are using the 8.314. So that number is in units of joules per mole degree Kelvin. Okay? Those are some funny units. Let's try and understand what that means. We have PV equals nRT. We have pressure in units of pascals times volume in units of meters cubed equals moles times joules per mole degree Kelvin times degree Kelvin. Okay? So which means on the right side of my equation I have joules, and on the left side of my equation I have pascals meter cubed. Okay? I know that my units have to agree. What is a pascal? Pascal is a unit of pressure. It's a unit of force per area. So, okay? So therefore, we can say that a pascal is a Newton per meter squared. And what is a Newton? It's a kilogram meter per second squared. Okay? That is our Newton, a kilogram meter per second squared, and we're multiplying that by 1 over meter squared. So therefore, our unit of pascal is going to yield us a kilogram per meter second squared. So if I then take my unit of pascal and I plug the fundamental units into it, I get that pascal times a meter cubed is equal to a kilogram meter per second squared times meter cubed, which gives me a kilogram meter squared per second squared, which if we remember from AP Physics 1, a kilogram meter squared per second squared is a joule. Our units agree. We have joules on the left, joules on the right. That is why it is important to understand your units, because my friends who've taken chemistry have a different value for R. The chemistry students use R equals 0.08206. However, that constant is liters, atmospheres per mole degree Kelvin. Okay? Their constant has different units. That's why the chemistry student constant is different. Okay? Moving on from there. We now have our gas law constant, 8.314, times temperature. Okay, and that equals big N, which is your number of particles, times the Boltzmann constant, K sub B, times temperature, equals nRT equals PV, which now we know is units of joules. And therefore, this is an equation of conservation of energy. This is an equation that defines how much energy is in the system. So we just showed you the Boltzmann constant up here, and we know that energy, joules, equals the Boltzmann constant, joules per degree Kelvin, times temperature. So this equation right here gave us the kinetic energy of a single particle, okay? Single particle, the kinetic energy of that one particle. If we want the kinetic energy of all the particles in the system, we're going to multiply the kinetic energy of one particle times n. And that's where that equation is derived from, okay? Again, all of these thermodynamic equations are in the top left-hand corner of the third page of your equation sheet. We are going to delve into heat transfer, okay? This is going to be a very introductory level of heat transfer. For those of you in college, there's going to be a lot of calculus heat transfer. It's a nightmare for those of you in college, okay? But we have it nice and easy here in the algebra-based physics too, okay? So you may have learned in elementary school that there are three types of heat transfer. You have conduction, you have convection, and you have radiation. Now here in AP Physics 2, we are largely going to focus our attention on conduction. It is the method that we have an equation for, okay? But just to reiterate what each of them are, conduction is the transfer of heat from one object to another by them physically touching, okay? You've heard the same example time and time again. If I touch a hot pan on the stove, I'm gonna burn myself because heat is being conducted from the hot pan to my hand. Convection, okay? Convection, let's give it a more rigorous definition, is transfer of heat from one object to another through a fluid. If you opened the oven, but you're not physically touching any of the walls of the oven, and you stand beside it, the heat from inside of the oven is being convected to your body because the heat inside the oven is being transferred to air, which, like we said, gases are fluids, being transferred to air, which is being transferred to you. Okay, so it's basically conduction by proxy. And radiation is a much more interesting form of heat transfer. Radiation does not require mass or matter at all. Radiation is in fact the way that heat from the sun reaches Earth. Radiation is heat in the form of infrared radiation, or infrared light, okay? I could go on and on about that, about the chemistry. Regardless, you don't need to hear me do that, okay? Let's focus on heat transfer with conduction. If I were given two mediums, let's say I have a divider right here that divides this big canister into two sections. Here in the left section I have gas A, in the right section I have gas B. Let's say that this center section is made up of some metal. Okay, so it's a solid that we don't know the identity of. Alright? If gas A is at temperature T sub 1, and gas B is at temperature T sub 2, and these temperatures are different from each other, then heat will flow from the hotter side to the colder side. Let's assume T1 is hotter. Heat will flow from gas A into the metal, and from the metal to gas B. If you want to understand more about why heat is being transferred at the molecular level, we cover that in the AP Chemistry course on the channel, the Ideal Gas Law unit. Again, if you want to learn more about any of this, just go check out the AP Chem video. Regardless, let's keep going. We have an equation that governs heat transfer, again, found with your thermal physics equations on your equation sheet, and that is Q over delta T is equal to Ka delta T over L. Let's explain what all of this means. Okay? Q, capital Q, is heat, or heat exchanged in this case. Okay? Change in T is change in time, of course. Notice what I did there. I corrected myself in writing that time is the lowercase t. Okay? You should remember that. Time is lowercase t, temperature is uppercase t. that will confuse you if you write both as uppercase T, because in this particular equation you have both present. Okay, so don't confuse yourself, don't make silly mistakes, and make sure to differentiate between your time and your temperature. Okay? Our small k in this case is a constant that defines our material being the thermal conductivity of the material. Okay? It's a constant, so it's either going to be given to you in the problem, or maybe you're doing an experimental design FRQ and you're asked to solve for the thermal conductivity given all the other values. Okay? Big A is the area. What do we mean by area? We mean the two-dimensional area that this gas is contacting. Okay? So if I were looking at the gas, if I were looking at the metal plate from the perspective of gas A, I would see a square, because this vessel is a rectangular prism, and this face would be the face that gas A is seeing of the metal separator. So in that case, our area A would just be the two-dimensional surface area of this metal conductor. Delta T, self-explanatory, is the change in temperature. Change in temperature between what? Between gas A, gas B. It's the higher temperature minus the lower temperature. In what? Degrees Kelvin. Okay. L, deceptively, is the thickness of the medium, of the conductor. So that would be this thickness right here. That would be L. So what does that tell us? It tells us that the rate of heat exchange, as what this left side of the equation is telling us, the rate at which heat is exchanged is proportional to the difference in temperature. It is also proportional to the surface area of the conductor, and it is inversely proportional to the thickness of the medium. Okay? I've been hinting at these since the beginning of the video, the 3 laws of thermodynamics. Okay? And you can hear my voice starting to become excited because I have a strategy for remembering these that I think you're going to like. Okay. Law number 1. Energy cannot be created nor destroyed. I'm going to write that as energy is always constant. Okay? Law number 2. Law number 2 is the entropy of a system, of any closed system, will always increase. Okay, and we're going to get into what that means in just a minute. Third law is you can never reach absolute zero, or Kelvin equals 0. You can never reach absolute 0. Okay? Conservation of energy. We've been learning about that since middle school. Energy can't be created nor destroyed, it can only change forms. We went into that in depth in Physics 1. Entropy will always increase. Now, this may be the first time that a lot of you hear the word entropy. Okay? And for those of you who took AP Chem, you probably have no idea what it is either, even though you've been dealing with it for the past year. It is the energy that is available to do work. Okay? So what does that mean? It means that in any system, in any exchange, even though the total energy remains constant, the total usable energy must always decrease. Okay? What do I mean when I say usable versus unusable energy? Electrical energy is an example of usable energy. You can use electrical energy to do work. All right? A reminder of what work is. Work is a transfer of energy into a different form or to a system. Okay? Work done on a system involves a force being applied to that system. So a form of energy that is usable can be used to apply a force to a system through work. For example, spinning a fan blade is an example of a force being applied to the fan blade and the fan blade spinning a distance. Electrical energy can be used to do work, and electrical energy can be used to spin the fan blade. So that's our example of usable energy. The overwhelmingly used example of unusable energy is heat. Okay? As you charge your phone, As electrical energy from the power grid goes to the lithium battery in your phone gets hot. Okay? Means some percentage of the electrical energy going into your phone is being converted to heat. Heat cannot be used to do work. Let me be more specific. A small amount of heat cannot be used to do work. If you have a massive, massive difference in heat, like I have 12,000 degrees Celsius over here, and I have 100 degrees Celsius over here, that massive difference in temperature can be used to do work to some extent. But the temperature differences that we see in our everyday life when we are converting energy cannot be used to do work. That loss of usable energy is therefore identified as an increase in entropy, okay? A lot of you know entropy as randomness. Randomness cannot be used to do work, okay? You need controlled, specific, compact, and directable energy in order to do work. Heat cannot be compact, directable, or specific. Therefore, heat cannot be used to do work, okay? If I am really hot on a hot summer day, that heat does not suddenly give me more ability to push a boulder up an incline. I spent a lot of time on that because entropy is a very confusing concept for a lot of people to understand. And law number 3, you can never reach absolute zero. Now, I remember these as the 3 laws of gambling. You'll never make more money than what you started with. You'll always lose. And you can never stop playing. Now, let me explain the context for the last one. If you reach absolute zero, if the temperature is 0, if you've reached absolute 0, it means there is no motion. If we return back to our kinetic energy of a gas example, we denoted that the kinetic energy of a gas is proportional to its temperature. If the temperature is 0, kinetic energy is 0, therefore the velocity of our particles is 0. If the velocity of our particles is 0, we are not moving. We are in a perfect stillness, a crystalline, immovable final shape. It's exactly defined as that, a perfect stillness, okay? It is impossible for anything in the universe to reach that point, okay? Well, you could cite the heat transfer equation as the fact that heat will always move in faster than you can take it away. Having a temperature greater than absolute 0 means you are always moving, always interacting, therefore always playing the game. We are going to look at the more practical problems and examples that you will probably see come up on your multiple choice and on your FRQs. Okay, in order to understand those, we look at the very common thing used in AP Physics 2, the PV diagram, short for pressure volume diagram, okay? So in order to understand this, we need to understand our work equation. On your reference table, you are given that the work done on a system is equal to negative P delta V. And I proved back when we analyzed PV equals nRT that PV is a unit of energy. The work done on a system is negative pressure times volume. Let's understand what that means in context. If I have a cylinder with a piston at the top of it, and I can push down on that piston, in this I have a gas, okay? And since I have a gas, and I am not at absolute 0, it means that that gas is exerting a pressure on the container, okay? If the gas is exerting a pressure on the container, it's exerting a pressure on the piston, and therefore in order to move the piston, in order for me to take my hand and push down the piston and compress the gas, I'm going to need to exert a force on it, okay? So if I'm exerting a force on the piston, and the piston is moving through a distance, I am doing work on the system, okay? So this is an equivalent of our force times distance from AP Physics 1. But work is only done on the system if you compress the piston, if the piston moves, if the volume of the cylinder changes, okay? Let me give you an example of a balloon, okay? If I have a balloon in my hands and I try to push the balloon, the balloon is going to get compressed where my hands are pulling it, or pushing it rather, and then on the other sides, up here and down here and all around, the balloon is going to expand outward. It's going to get squished, okay? So even though I'm applying a force to the balloon, even though I'm moving the balloon a distance, whatever volume was lost as I compressed it in this axis is volume that the balloon gained by expanding outward in the other two axes, okay? Usually you're going to have to deal with a relationship between pressure and volume. So if, let's say, my relationship between pressure and volume looks like this, and the problem asks me to find the work done on the system, we're going to have to reintroduce a process that we covered back in AP Physics 1, the area under a curve. The area under the curve is the x-axis multiplied by the y-axis. Okay? So multiplying volume times pressure gives me the area under the curve. Okay, therefore the work done in this example would be, if this was a volume of 10 and this was a pressure of 10, the work done on the system in this case would be 10 times 10 over 2, which would be the area of this triangle. Okay? That's how we use the PV diagram to determine work. Okay, but why is the negative here? Is probably what you're asking right now. Okay? Let's say that our pressure is a constant pressure. Okay? Therefore, if we're dealing with work being done on a system at constant pressure, if I decrease the volume of the system, if I am putting a force on a piston to decrease the volume of a system, then my delta V is negative. If I decrease the volume of a system, I push on it, my delta V is negative. Okay? But if I decrease the volume of a system, I am doing positive work on the system. Okay? Which means a negative delta V needs to equal a positive work done, which is why this extra negative is here. Okay. Now from there, we need to cover the 4 types of processes that we do with gases here. Buckle your seatbelts because this is a real headache. So I am going to constantly refer back to this figure that I'm drawing right now. And this is probably going to be the setup that you're going to see on every AP Physics 2 problem you have concerning this. All right? It's going to be some gas in some cylinder with a piston on top. Okay? Piston on top. Now, there are 4 general types of processes that we're going to undergo on this cylinder. Okay, the first type is called the isobaric process. Now, like all the processes, you can have an isobaric expansion or an isobaric compression. Okay? So the type of process is not indicative of the work being done, but rather it is indicative of the conditions in which it is being done. An isobaric, by the way, you're going to have to memorize the names of these. So you're going to need to memorize the name and the conditions that it corresponds to. An isobaric process is, as I've written here, where the pressure of a system is constant, is held constant. If I were to do an isobaric compression, as I were to lower the piston, as I were to compress the system, even though it's being compressed, the conditions are such that the pressure is held constant during this compression. Okay? In an isobaric expansion, the opposite is true. If I release the piston and I allow the gas to expand, I allow the gas to exert a force upward on the piston and move the piston upward, that is an isobaric expansion, during which the pressure in the canister is held constant. Now, in order to analyze our gas processes, we're going to need to take in 2 of the equations from our reference table, and that is the one that we covered before, that work equals the negative change in pressure times the change in volume. And the new one that is unique to here is that the change in U equals Q plus W. Okay? What is that? Delta U is the change in internal energy. Okay? Internal energy might seem to you as a pretty ambiguous term, but all you need to know is that internal energy equals Q plus W. It has no significance to you apart from that. Change in internal energy equals Q, which we covered in a previous equation. Q is the heat, or the change in heat absorbed by the system, where W is the work done in the system given by that equation. So therefore we can rewrite the change in internal energy as Q minus P delta V. I want you to look at Q and understand that that does not mean heat energy. It means change in heat energy, okay? That means that, as we will cover in later processes, if the change in temperature of your system is 0, which means if your system's temperature doesn't change, your Q is 0, okay? Let me reiterate. This is not total energy, this is change in heat energy. So let's consider this equation in terms of our isobaric process, all right? Meaning that our delta U is equal to our Q minus our constant pressure times our change in volume, okay? Let's interpret this with respect to a PV diagram, pressure volume diagram. If pressure is constant, that means that we are looking at a horizontal line, okay, because pressure can't change. So if we want to find the work done on a system between an initial volume here and a final volume there, we would find the area under the curve between those 2 points. That is a horrible line. Let me try and draw better. There you go. The work done on the system would be this area under the curve. Whereas if my pressure were not constant, pressure might vary with respect to a volume like this, or like that, or you get the idea. In this case, pressure is a flat line. But in this special case where pressure is constant, the work done is equal, can be calculated using this equation, okay? But when pressure is non-constant, the work done can only be calculated using area under the curve. The next type of relationship is the isothermal process. Isothermal, as you might expect, determines that our temperature, our change in temperature rather, is 0. Isothermal, the temperature of our system doesn't change. Now, an interesting characteristic of internal energy is that our change in internal energy is proportional to our change in temperature. Consequently, our internal energy is proportional to our temperature. Okay? Therefore, isothermal, given this relationship, says that if our change in temperature is 0, it means that our change in internal energy is also 0. So therefore, when we pull down this equation, we say that 0, our change in internal energy, equals Q minus P delta V. Okay? But be careful, because in an isothermal process, you probably won't have constant pressure. Therefore, this term, the work, can only be determined with area under the curve. Okay? The characteristics of an isothermal expansion or an isothermal compression indicate that it must happen over a very, 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 very long period of time. Okay? Why is that? Because you need to allow enough time for the heat of the system to dissipate. For example, if I were to take my piston and force it downward really fast and compress my gas, I would be doing work on the system. And if I'm doing work on the system, I'm increasing the internal energy of the system. If I'm increasing the internal energy of the system, I'm increasing the temperature of the system. Therefore, by forcing that piston down, the temperature of my system is increasing, okay? So I need to allow time for any temperature increase or decrease to diffuse away. So an isothermal mechanism, an isothermal process would be done with heat dissipating elements around it. Such that if we were to draw a PV diagram for an isothermal process, the PV diagram would look something like that. Something like 1 over x. Since you guys don't do calculus, you are not going to be able to find the area under the curve. But something interesting we can do is, since we know that our temperature is constant, nRT equals PV, N is a constant, it's the amount of moles in our gas, and this is going to occur in a closed cylinder, so there's no adding or removing of gas. R is the gas law constant, a constant, and in this case, our T, our temperature, is not changing. Therefore, we can say that some constant value, C, which is the product of 3 constants, is equal to PV. Therefore, PV is constant. This equation is pressure times volume, where this equation is pressure times change in volume. Okay? So even though this might remain constant, this doesn't have to. Third one is the isometric process. Isometric process is the characteristic that your change in volume equals 0. If we look at the work equation, if change in volume equals 0, that means work done equals 0. Okay? So if we look at our internal energy equation, we know since work done goes to 0, our change in internal energy is only equal to the heat added to the system. Okay? How is heat going to be added to the system? I don't know, you put a fire under it. Okay, that's an example of heat being added to the system. The gas is currently undergoing an exothermic chemical reaction. Okay? Heat can be added to the system in multiple ways. Maybe you might need to understand how to convert temperature to energy, because internal energy is in units of joules, because it is a quantity of energy. And you are going to be given changes in temperature. So from changes in temperature, you are going to have to use the kinetic energy of a certain particle equals 3/2 k sub b times t, and the total kinetic energy of all particles in the system equals the kinetic energy of each particle individually times the number of particles. That is how you go from temperature to heat energy, because the total kinetic energy of all particles in the system is equal to the heat energy of the system, H. Or rather, you could say the change in heat of the system is equal to this times the change in temperature. So those are your conditions for isometric, and then last but not least, you have adiabatic. Adiabatic means that the change in energy, of heat energy of the system, Q, equals 0. Okay? Like I said before, Q is not the total heat energy, Q is the change in heat energy. So the change in heat energy of the system equals 0. Notice the difference between isothermal and adiabatic. Okay? Isothermal meant that the change in temperature was 0 of the system, okay? But if we're looking at, let's say, an isothermal compression, a compression is adding heat energy to the system. Therefore, in order to characterize an isothermal process, the compression must be adding energy to the system, while some other methods are taken to remove heat energy from the system, okay? Therefore, Q is non-constant here because heat is moving in and out of the system. But you don't notice heat moving in and out of the system because the total heat energy delta T is constant, or the change in heat energy delta T is 0. Adiabatic means there's no flow of energy in or out of the system. Okay? So if we consider an adiabatic compression, it would happen very, very, very fast, because we don't want to allow time for heat energy to leave or enter the system. That's the difference I want us to realize, the difference between temperature and heat energy. You should look up on YouTube videos of adiabatic processes. They're pretty fun to watch. There's like a little explosion, but I'll leave that to you. If we take a look at our PV diagram is going to look a little something like this. It's going to look like the isothermal, except it's going to be much steeper. So if we were to draw a PV diagram and describe all of our processes with it, we have the isobaric process, where pressure is constant, the isothermal process, which looks like this, the adiabatic process, which is again going to be a much steeper form, and of course you have the isometric. Okay? So let's take a look at what isometric might look like. If the work done on a system is 0, and the area under a PV curve is 0, that means that our PV diagram for an isometric process is going to be completely vertical, a vertical line. That means that if we try and calculate the area under a vertical line, we're going to get 0, because when volume is constant, your work done is going to be 0. Okay? That should be all of thermodynamics, guys. Again, if you need more practice, you're going to go to Khan Academy. They have some lessons on this. If you have questions, if you need extra practice, extra help, some tutoring, you're going to join the Discord server, linked on the channel page, linked down below. Come talk to me. I'm here to help you. Good night.